Hey everyone, so I just want to go through an example of showing that a function is continuous at a point since we didn't get a chance to do one in class. So this is the question we're going to look at. Show that f of x, which is equal to the absolute value of x minus 3 plus 5, is continuous at x is equal to 3. Okay, so first of all, what you're going to notice here is that since this is an absolute value function, it can be rephrased as a piecewise function. And that's going to be important because since it's a piecewise function, you might consider whether or not it is continuous. Now, of course, this is a transformation of the absolute value function, so we probably already have this understanding that it is a continuous function. But I did want to show you an example where we're dealing with a piecewise function to begin with. So what I think we should do is we should start by writing this function as a piecewise function. Okay, so let's see, we have f of x, which is equal to the absolute value of x minus 3 plus 5. And as a piecewise function, well, let's see, when x is 3 or more, the absolute value bars are not really going to be doing anything. So what I'm going to do is I'm going to write that as just x plus 3 plus 5 if x is greater than or equal to 3. Now, when x is less than 3, then the absolute value bars are going to be swapping the sign of everything inside the absolute value. So what that means is that we're going to be multiplying all the stuff in my absolute value by -1 to swap the sign. So that means that we're going to have negative x plus 3 plus 5 if x is less than 3. Okay, great. So now that we've got this written as a piecewise function, we want to show that it's continuous at x is equal to 3. So if you remember, we discussed in class that for a function to be continuous at a point, there are 3 criteria that have to be met. First of all, the limit at that point has to exist. Secondly, the function must be defined at that point. And then thirdly, the limit at that point must be equal to the value of the function at that point. And that means that we're going to have to show each of those 3 properties, we're going to have to show that each of these 3 properties is true for this particular function. So first of all, let's start by showing that the limit as x approaches 3 on our function exists. And to do that, since this is a piecewise function, we are going to have to split this into the left and right hand side. So we're going to start by finding the limit as x approaches 3 from the left of the absolute value of x minus 3 plus 5. Okay, well since we're approaching 3 from the left, that means that we're approaching it from values of x that are less than 3, which suggests that we could use the first expression in our piecewise function to evaluate this limit. So we get the limit as x approaches 3 from the left of minus x minus 3 plus 5. As you're going to notice, this does simplify. So this should simplify to the limit as x approaches 3 from the left of negative x plus 8, right? Because the negative multiplies with the x to give us negative x. Minus negative 3 is positive 3, and 3 plus 5 is 8. And this is actually something that we could evaluate simply by substituting. So we're going to substitute the 3 in, which gives us minus 3 plus 8, which of course gives us a value of 5. So the left-hand limit gives us 5. Let's check the right-hand limit. So the limit as x approaches 3 from the right of absolute value of x minus 3 plus 5. Well, if we're approaching 3 from the right, we're approaching 3 from values of x which are greater than 3, which means we can use the second expression to evaluate this limit, which means we have the limit as x approaches 3 from the right of x minus 3 plus 5. This, of course, is also going to simplify. The negative 3 and the 5 are going to add together, right? And we're going to get the limit as x approaches 3 from the right of x plus 2. This can be evaluated using a substitution as well. So we're going to have 3 plus 2, which, of course, evaluates to 5 as well. Okay, so what you're going to notice is that the left-hand limit and the right-hand limit do give us the same value. Well, we should know what that means by now. That suggests that the limit as x approaches 3 of f of x is equal to 5. And of course, if the limit is equal to 5, we know that the limit exists. So we've met the first criteria, that the limit as x approaches the value that we're looking for, in this case 3, of our function is defined. All right? The next criteria that we need to come up with is to show that the function is defined at the point we're talking about. So that means we need to know that f of 3 takes on a specific value. So what we're going to do is we're going to plug in x equals to 3 into our function. So that gives us the absolute value of 3 minus 3 plus 5. Well, 3 minus 3 is 0, so we have the absolute value of 0 plus 5. And of course, absolute value of 0 is 0, which means we just get 5 as our answer. Okay, that's the second criteria. And also, I guess in a sense, it's the third criteria as well, right? Because we showed that the limit as x approaches 3 of f of x is equal to f of 3. Okay, so again, we've shown that the limit as x approaches 3 of f of x is equal to f of 3, right? And this was the third criteria that we had for a function to be continuous. That means we can say, so f of x is continuous at x is equal to 3. All right? And this is how you show algebraically that a function is continuous at a point. Anyways, take care, guys.